Okay, so as I mentioned today, I'm going to start to, to teach how to model surfaces, right? So this is, as is mentioned in the manual. If you read carefully this, you are going to see that we need the information of the bulk structure. So we need, as you can see here. So what we're going to do is to replicate this step by step. So the first stage is to take the bulk that we computed, right? Ready from the calculations. We are going to, first of all, to find from the primitive cell, we're going to apply symmetries and to get the unit cell. So the cube is the unit cell. So we build surfaces from the unit cell, not from the primitive cell. Okay, that's the first step. Second is we're going to cut along either 001, 1100, or 010. It's 0, 0, 1, 0, 10, so are equivalent to get this, as you can see. So the first, I think is how many layers we're going to use. We are not going to test this because it's extra work, but it's okay because the main you have to use. In fact, we should use an infinite amount of layers to define a proper surface. But we cannot do that, right? So other studies, we are not going to do here, but you have to keep in mind that there has to be a certain number of layers. We're going to see in a moment in Material Studio that allow us to emulate the surface. What does it mean? It means that, for instance, when the surface is done, here, that's where we compute the surface. The electrons here doesn't know that there is an end here on this surface. So that is so with this thickness, we try to skip or try to eliminate any kind of quantum confinement. So when the thickness of the slab, here we go the same. These two things, there might appear some quantum confinement. This, I mean, it is a real effect, a quantum effect. But in our case, since the layers experimentally they use very thick, I don't know, maybe hundreds of nanometers, that is the reason that we cannot do the thickness of these hundred nanometers, right? So we have to do a compromise. That compromise is just to check the convergence in the total energy with the number of layers. I'm not going to do it here, just in case you want to know how many layers I have to pick up. In the literature, you're going to see that this surface is for this case of surface for silicon FCC with 5 layers is enough. Okay, so okay, that's the thing. So let's start to the learn. So I'm going to teach you, and I'm going to explain as many times as you need to do this. Okay, so if you go to the manual, so we have to build up this slab. So this is our starting point will be the primitive cell. We have to get the unit cell and after to build up the slab. Okay, so it says first of all, look this. We go to the directory one, part 8 ML. So this is part 8 ML, by the way. So it's here. Where is this? Here, right? So I'm here. And look, I have this postcard bulk. Okay. So this is the optimal postcard file that we have found using previously DFT. If you check this, what is postcard bulk? Look, this postcard bulk is this. See? So this is the optimal we found from the connection we did previously in previous section. So please, what we're going to do is to convert that postcard bulk to a bulk, a .zip file. So please just copy this and paste it, right? So we have to build up this and we are going to do this, okay? So now we have a bulk.zip, you see here. If you want to check what is this is a typical zip file that I believe that we already check this, open with, you see? This is a typical zip file, and as you can see, this is you see the structure is a primitive cell, it's not a unit cell. Okay, now the next task is to open Material Studio, and we have to create, the file called sf110.zip. So this is the slab we want to compute. Okay, so
I'm going to follow. I'm going to do very slowly, please. If somebody wants has any question to repeat this, just please let me know. I'm open. Please, everyone, open Material Studio. Okay, I'm going to pause here this. Okay, so now the my interface is open. Look this. I recommend to have this in project and properties, right? So these two. Okay. So now I'm going to import here. See, I'm going to import with this icon, or you can go to File and you say Import. Okay, you see it's the same. So I'm going to use the icon, so it's the most handy. And now I'm going, where are my files? So in my case, I connected to this. In my case, is here. Part 8, bulk, you see? This is a zip file, you see? This zip file. I enter, open. There it is. Okay, so I'm going to wait. Okay, so this is the structure we computed in VASP, by the way. So the first thing is, as I mentioned yesterday in the this, please try to open with this. We are going to manipulate the style. So here it means, you see, it says it's display a style. So you open this menu and you are going to see these options here. Please choose, okay, please choose this, please, bulk and stick. I choose this, and after I put this, okay. Now I need to see also the when it's with the sticks the bonds, right? So this is very handy. How to activate the bonds or how to to include the bonds is with this, this here. Calculate bonds, you see, with this here. Calculate bonds, and you get this. Okay. So that it is the structure. So remember, this is the primitive cell of the structure. It has only two atoms, right, in total. Next, please, we're going to compute the symmetry. Look this, with this icon here, it says find symmetry. You see these icons here, there is this kind of icons, ABC, this same in the same menu, okay? So I put this find symmetry and put the symmetry, the tolerance, put 0.001, 10 to the minus 3. Find symmetry, and there it is, you see? So my system is a FCC with the IT numbers 227, and this is the parameters of this. If you say impose symmetry, please, you have to impose symmetry. There it is. So you get this structure. See? So you are changing from the, if we apply symmetry, but this program will give you automatically the unit cell. Okay. Now, since I need to orient it in a proper way, so I use this, please, here. You see, first of all, we go here in ABC, in lattice parameters, you see, you put this, and you put this, right? So this in advance here, parameter, you see the parameters are here, right? This is the parameters of the cubic cell. You see alpha, beta, and gamma is 90 degrees. If you go to advance, you please check the cell origin. So we are going to fix to the origin, the cell origin will be 0, 0, 0. You see? There it is. And after that, we put reorient to standard. Okay? So this is a cell where the origin is put in in 0, 0, 0. And after when you press home, the 3D viewer reset view, you are going to see this. There it is. Okay? So the next step is to create the surface. So I'm going to here in build, here, you go to build, and you go to surfaces, you see? Surfaces, and you're going to clip surfaces. Surfaces, clip surface. So we want to do this. Surfaces and clip the surface, okay? So let's click the surface and let's leave it like this, This let's do it as it suggests the Material Studio. It suggests that it is going to clip the 001. It's okay. So 001, 100, or 010 is the same. So I leave it like this, clip it, and there it is. You see, I have my slab. See? There it is my slab. Okay. So the next step, what it will be the next step is to put a vacuum, and that with that we are going to have my new structure to compute. So after this, you build, okay, if you like, you can close this, and you build the surfaces, the crystals and vacuum slab. Build vacuum slab, leave it like this. So by default, it give you 10 Armstrongs thickness. So just leave it like this because we are going to manipulate later and build. And that's it. You put home, and before we finish, please, we're going to set up the origin to 00. So you press again A, B, C. Do this. In advance, you put 00 and here 0. Reorient to standard, and that's it. When you put the house, you get this structure, and you go to the arrows, you see, there it is. Okay, I'm going to pause here. So when you build the slabs of surface, and in this case slab because it represents space. First thing is that you have the structure you computed, you have to put it to put symmetries, right? And to get the unit cell. On the unit cell is where we start to cut the system. Otherwise, it's going to be a no possible, right? Or you're going to get a different type of surface. Okay. So once we have the symmetries, you cut, you clip the crystals, and you start to get some slabs. As you can see, this has 1, 2, 3, 4, 5 layers. You see? So if you like, well, anyways, it has 5 layers. I forgot to mention this, right? So in this case, automatically it gives me 5 layers, so it's okay. Otherwise, you have to increase this. Okay. So if you like, I can repeat very quickly this. So I'm going to repeat this, please. So you see here in my left hand, I have the models, you see? I'm going to come back to this model. I'm going to clip again, right? So I'm going to build surfaces, clip surface, and I'm going to clip this, and look this. So I can increase the number of layers here. So or decrease, for instance, you can decrease like this, with this, the thickness, right? So like this, you can increase to less, and so on. So in this case, the slab will have 1, 2, 3 layers. You see, you start to increase to 4 layers, 5 layers, 6 layers, and etc. etc. So the thing is that if you want to know what is the thickness you have to use, you have to create several systems with different thicknesses, and after to check what happened with the electronic structure at the surface of this. Anyways, okay. So that is just for your information. So I'm not going to use this. So I'm going to erase this, like this model here. Okay. Okay, so we created this. Okay. So next step, look this. When you press home, you see when you press this icon 3D viewer reset, you have to see this. See? So it means that in my case, as you can see, it is in this kind of structures, you have two kinds or two surfaces, as you can see. The surface that is here and the surface that is down here. Why I'm saying this? Look this. If you check here the display style and you increase the thickness, the repetition along Z. You see? There it is. You see? So in fact, you are computing this structure, and of course, I can do in the other directions. Let's say like this. So you see, we're going to compute this structure, and in fact, how we're going to use the results of this structure versus the actual surface. That remember, the surface is infinite deep, and we are going to consider this to be the surface. Therefore, we have to be later. We're going to check how to make this or how to find out the distance between this and this. So we go the vacuum or such a way that
energy, it is, it is in fact not changing. So we don't need, or the energy, the cell interaction of this energy, this stuff with this has to be neglected. So that is what we want to check, okay? So with the same convergence criterion of PV. Okay, so that is just for your information. Just to, you can play with this, but at the end, what we want to compute is this one by one, right? So there it is. So after this, we have, it says the manual says save this structure as a uh, SF100CIF. So I'm going to file, export, and I'm going to put here, in my case, I'm going to put in desktop, please, because in my case, I cannot save directly to my so SF 100CIF. Okay, and look this here, you take this Atomistic Material Studio. So I'm going to take this here and I put a zip file. Where is this zip file? Is here. And you save it. Okay. In case I was. Okay. So I'm going to pause here. So I'm going to repeat here because I'm recording. So I just saved this file. File. And you export this, export, and I'm going to export like this, SF, sorry, like SF 100.zip, you see? And look this, the type of format is here, right? It's a crystallographic information files.zip, okay? Save it, okay, since I already, it's okay. I'm going to replace this, okay? So you have to copy this file inside of your work directory where you're working with VASP. So in my case, I'm just, I just copy here, you see, in my work directory here. So I can see this in my directory. So look this, I have my SF, this file, okay? Please, everyone, till here, I'm going to. So now I'm going to convert this SF100.zip to Postcard 100. So I need in Postcard file format. So how to do this, please? You enter this command and you get this, okay? So that's it. So don't worry about this, my warning. And if you want to check that file, you can say this, CQ, and we have this. So this is the structure which as we created with VASP, okay? With Material Studio. So this is my slab. Now I can even see this in the Postcard file format. So it means that I would be able to start to compute using VASP from this. Okay. I'm going to pause this. So now, first thing is before we run, we do the calculations, we have to check what is the K-point grid that we have to use in this calculation, right? So that's the reason why I'm going to open here and so I'm going to put this subsection, this because check the K-point grid. Okay, so I'm going to put here as a subsection, and I'm going to check this. Okay, so we're going to check what is the K-point grid. First of all, I'm going to check, for instance, what is the unit cell. The unit cell is equal to this import, right? I'm going to take only this. Before we continue, please, I'm going to set up the work directory, right? So here. So please don't forget to put this to be point out to this directory here. Now I'm going to check this import postcard
bull, right? There it is, comma, table. See, this is my poster, right? So the lattice of the unit cell will be this. If you see the unit cell is this, right? I need the lattice parameter is this multiplied by this vector 1, 2, 3. So A, B, C multiplied by this. So the lattice, I'm going to put the lattice of my unit cell is equal to this, equal to this unit cell. This is 1, 2, right? So we get 2, comma 1. So this 2, comma 1 is this value multiplied by unit cell of the 3 at 5. Like this. Okay? We have this. So I'm going to say that A, comma B, comma C is equal to this. So I have my lattice vectors. You see, lattice vector. This is of the primitive cell, please. Now what we have to find is the following, right? So I'm going to check this delta K. So this is delta K is the increment in the reciprocal space, something that we are going to check later this week, I think. 0.08 till minus 0.005 times I. So this is the to check the some list of increments. I was from 0. So this is my delta K. Now please stick with me. I will explain what I'm going to do here. Okay. So I'm going to do the following, right? So I'm going to map. First of all, I'm going to do the following thing. Hashtag, comma, and now I'm going to do the following. Round. I'll explain why I'm doing this. B plus C divided by A plus B dot right. This is the first, the second, and this divided by, and all of this divided by hashtag. Okay. I'll explain in a moment what I'm doing here, please. So just stick with me. Just copy this here, paste it here, and put round A cross C. Wait. No. And finally, round A cross B. Okay. Comma, hashtag. Here. Okay. So we have this. So as you can see, these are what we define the reciprocal lattice vector, right? So in fact, this just to remind you this, just to inform you about this, right? Going to pause this. So just to inform you of this, so sometimes we call A1 is equal to 2 pi. So in fact, the definition is 2 pi B cross C, right? Divided by, so this is a lattice vector, by the way, divided by A cross B dot C. So A2, oh, sorry, A, B is 2 pi is C cross A divided by A cross B
dot C and secant, you see, the reciprocal is 2 pi is A cross B divided by A cross B dot C. These are the reciprocal lattice vectors, as you can see from this cell. So what we need is, as you see, I take the norm and after I divide by hashtag. So it means that what we want to see is of the length of this reciprocal lattice vectors, how many sections we can get from this delta. And that will give me the grid, right? So let me check this. If you do this, you are going to get this, you know. So remember, in our calculations, we found that the grid that converted the total energy for conversing the total energy was 0.025. So this delta K is very important because we're going to use exactly the same delta K in any kind of system that we are going to use right now on C. Delta K. So we keep this value, not the grid, because the grid it is for this primitive cell was 999. Remember what this is. So it means that I want to know what will be the grid, for instance, for this new cell that we just created with 999, I mean with 0 from 0.35. So we want to check what should be the grid, okay? So that is the the task, right? So let's go this slab. I'm going to import, you see, import. So I'm going to import the postcard file that we created, postcard, you see, comma, postcard. Okay. And now I have the lattice will be this, right? Slab 2,1 multiplied by slab 325. So this will be, in other hands, the lattice parameters of my structure of my slab, say 107. See? X, Y, and Z. So I'm just going to copy this again, please. A, B, C. So this A, comma B. See the lattice parameters equal to this. That. Right? And I'm going to repeat same here. So I'm going to copy this. Okay. And this. The same is. See, same delta K and this delta K. And now I have, since I have this new, I have this. You see? So for delta K, that we know with delta K 0.035 is the convergence that we already computed previously in the beginning of the, when we computed the bulk of silicon. It means that to do at the same level of convergence, we have to use this 772, right? But in the case, since we don't want the interaction between these two slabs, we always going to use, in this case, because the slab is the surface along 3, the number 2 is we're going to replace by 1, because we don't want the interactions to take into account any interaction in the Z direction. In fact, if you use bigger, you say, but maybe they increase the precision. In fact, it's not correct because you're trying to capture the interaction between the slabs, and that is not problem. That's the reason we use here a 1, this dimension. Even though that here, yes, I show you that it is 2, but we're going to check 2, 1, please. Okay. Questions in here, please. Questions? Questions in here? Somebody, please. Questions? Okay, I'm going to pause. Now I'm going to check the grid we use to train the force field. So why I'm doing this? Because I have to use the same equivalent grid to compute the, in this case, of the calculation, right? So let me see this. So lattice supercell to this.
cell 2.1, cell 3 to 5. There it is, right? I'm going to copy back this again, this ABC, ABC, C is equal to this. And now I'm going to copy this delta K, the same, delta K, the same, and this is this. There it is. Okay, so everyone please still here. Okay, so as you can see, the grid that associated with this delta K is the 2 by 2 by 2 is 0.75. So let me check now in my postcard. So what does is equivalent is equivalent to 3 3. See? So if you want to compute with, if let's suppose if we want to do an ab initio calculation in VASP, we have to use this grid. But here we have to put one. But since we're going to use the machine learning, we have to use the same grid, equivalent grid we use for the machine learning, the one on 7.779. It's equivalent to 2 by 2 by 2 in the supercell of 2 by 2 by 2. And here will be 3 3 1. So that is the grid we have to use if we want to use machine learning. Okay, so just repeat again before I'm going to do the calculation. You have to be careful with the grids, right? So if I'm going to compute only the ab initio, pure ab initio VASP, this cell, I should use this. 771. Remember, this has to be always one along this. In this case, it's one because by constant, but anyways, always we have to do one. But since in our we want to do this with machine learning, in machine learning we use a postcard file that was 2 by 2 by 2. This the 2 by 2 by 2 was equivalent to 0.75. So for that reason, we have to use this 3 3. So that will be the grid we're going to keep in our calculation, and it's mentioned here, right? So we use the delta K we use for the machine learning was this 0.075. So this in my grid for the slab is going to be 3 3 1. Okay. Here, very clear, please. Use always in the Z direction has to be always one. Whatever it happens has to be one. Okay. What else? Uh, we're going to run the vacuum.sh. Please open the vacuum.sh. Look this. We're going to run this, okay? In my case, I'm going to put again only 2 cores, please. You will like you can keep this. In my case, I'm cores. Just to make it not, I mean, anyways, the calculation is going to be very fast. Okay, so look this. So first of all, what is going to do? It's going to create a directory called surf, first of all, and after it's going to move to surf, and we're going to put this parallelization. Next is going to copy from ML, you see, the force field ml hyphen fn, right? So we have this already computed from the previous section. Now look this, the cap points. So there is a cap points ml one by one. So let me check what is the cap points ml one by one. Here it is. So the cap points is exactly what I mentioned before. Is the one that we're going to use, that we computed, in the equivalent for from the machine learning postcard file that we use 2 by 2 by 2. The grid is equivalent to 331 for this calculation. So it's going to copy this. It's going to copy the Incal MLST. Well, let me see what is Incal MLST. Is this one, please? That is the Incal MLST. Look. So this is, so basically we're going to use the machine learning, the force field that we're going to in this system. No, that is very interesting. Okay. So we're not going to do an ab initio calculation right now. Okay. And finally, we have to use the podcast file that we already here. Okay. So look, this is going to start a series of calculations with this index in here from 5 to 15, right? And here you see the top is this. So let me see this from the postcard file 001 we created. The top is here, right? Look, this is here. So it's the same. So it's here. And besides, I just copy and paste this, postcard 01 within this script. You see, it's exactly the same. No changes. So I adapted this, I did it just so you can see you don't have to do, this kind of step. So basically what I did is I copied this part of the postcard file we created here inside of the script, and I just changed the labeling here, and that's it. So now it's going to, every step is, you see, is going to change the C value. So that is the vacuum. But what is the vacuum is this value plus the top, the top of the silicon of the atom in the silicon slab. You see, it makes sense because if I will open this. Let me see. Let's see. Is this? Look this. What I'm doing is this. Just to explain. So the top atom is this. So in my calculations, I'm going to do this. I'm going to create a length of this from here to here, from here to here. I'm going to increase, let's say, I will start with 5. So I will increase here plus 5. So my lattice will be from here to here. You see? So in every step, I'm going to increment the value that's mentioned in this script plus the position of the topmost atom, right? So what is the script? Is here, right? You see, next is 6. You see, next value is 6. So it means that when you come here, I will put this atom, the 6 atom here. So you see, well, I'm going to do a series of calculations where the vacuum is this value, but the lattice parameter is this value plus the topmost one here, because this atom here is in the origin, right? So I'm going to basically, I'm going to increase this length of C and to see what is the conversion, right? Because you see this atom here, this slab is interacting with this other. What is the image? The smaller it is, the bigger is the interaction. So basically, I want to see what happened with that self-interaction with the increase. I have to find some conversion, right? Some plateau. In that case, we say that the self-interaction is neglectable and that's it. Okay. So let's run it, please. Let's run it this script. So the result will be put in vacuum.dat. Okay. So just you have to run this. So let's run it. Just in case, please check that you have this file in case this ML. You have this this ML-FNN. So let's see if it exists. See, here it is, right? FFN. Look this, that is the force field. Sorry. This is so slow this. Here's the force field, as you can see. So that force field, we're going to make a link in a new directory called backend. Okay, so let's run it, please. I'm going to close this. And let's run it. Okay, so I'm going to run this vacuum message, right? So you don't have to touch anything because I created already the files that you need. Okay, so it's running. I suppose I'm using only two processes. That's it. I finish. It is finished, okay? Very fast calculations, as you can see, because we're using the force field, and that's it. Once the calculation is finished, please, you have to get this file. Oh, 1 second, please, and my computer is almost. Let's see what is the output, please. On Surface, you have to have a file called vacuum.dat. And there it is. So you get these values, okay? So those are the values that you get from the calculation using the one. Okay. So we are going to anyways, everyone till here, please, you have any question? You get some similar values, good? For different values, good, because in the postcard. Okay. Or what is it? No, that doesn't matter because this is different. It's very strange, but you can see, anyways, we are completing this with this thing. You run this thing. Yeah. And that's it. So the point is you have to come top as we said is in minus. It's basically that's it. And this is 83 and this is 14. Just let me check this. Okay, so I'm going to pause this here, please. The change, we're going to the change of energy per atom versus the vacuum size. Okay, so this will be a subsection. Okay, so let me take this. In my case, the vacuum is equal to import. I'm going to import this surf, the folder surf, vacuum. That after I'm going to do map. So I'm going to do, I need to, since the system has 5 atoms, so I have to do the first one, 5, hashtag. So these are my values, okay. So what I'm going to do is to do a list plot, okay. List plot. Okay. Frame from. Okay, nothing else. Sorry, I think I have some parameters already set up here. Is this yes? Family, yes. Yes, I have this. Comma. Yes. Frame level. Going to put like this, vacuum. Energy in electron volts per lambda. Sí. Comma. Access. Bounce. Param plot. Param plot. We have to check this. Remember param plot. We have this parameter here, by the way. So just you have to shift to put the memory back this time. So if you like, I can copy this here, just in case the param plot here. Okay, so param plot. So I copy paste of this param plot that is in the beginning of this book or this section. So comma plot range all comma minute 2 comma epilogue ref comma absolute point size 6. Like this. Okay, this is my calculation, please. Everyone, please. I want to see yours. Okay, I'm going to. Okay, now we have to check from which value of the vacuum we have already convergency. So let me see here. I'm going to use this. I'm going to plot this. Let me see I'm going to plot from 8 and above, right? So I'm going to put let's put this from the last value plus, okay, plot range. I'm going to put like this. Well, last value of vacuum. To this, you see that is the value plus 10 to the minus 3. So as you can see, from the 8, basically from 8 angstroms, we already have a convergence of 1 meter. So it means that the self-interaction between that slab is already reflective from 8. So we can use from 8. In our case, we're going to use 11. Why? You could use 8 and you will find 11. Why? Because we want to simulate S-beam image. For S-beam image, we need an extra vacuum to study what is happening with the wave functions of the function of electrons in the record. Okay. So anyways, is that clear, please? I'm going to stop here. Okay, so I'm going to stop here.